how do you look at a signature like that in the metabolites coming from the body?
Yeah, absolutely. So one thing that, for instance, we'll do is let's just talk about the cancers. And we have everything in here from thyroid cancer to pancreatic cancer to breast cancer. A lot of my own work is in cancer, so I can speak to it really easily. And I've most of my publications are in cancer detection and the development of biomarkers for breast cancer and et cetera. So let's talk about cancer. One of the most telltale signatures of cancer is what's known as the Warburg effect. Of course, named after the scientist who discovered it. And the Warburg effect is essentially a process of anaerobic glycolysis, whereby the cells will increase use of certain substrates, even in the presence of oxygen. But that's not the important part. The important part is that we'll see disturbances in the TCA cycle intermediaries, specifically citrate and succinate. We'll see increases in oxaloacetate. What's basically important to know about these metabolites is that they're really essential for the tumor's growth and angiogenesis. So before the tumor sort of metastasizes and goes elsewhere, and we find signatures of it everywhere, what it's trying to do is it's trying to recruit certain metabolites, because those metabolites are really important to be the building blocks and the sort of pathogenic machinery the cancer tumor needs to build to become, metastasized, to sort of recruit its own blood supply and to feed itself and continue growing. It's a really devious but elegant process. And so by monitoring subtle but consistent elevations in some of these TCA cycle metabolites, we can sort of pinpoint and infer the progression of maybe a tumor. And it can be a tumor of a non-specific origin, but a tumor nonetheless. And those, according to our data that we published on, those signatures can predate stage 1 breast cancer even. So you could not even have a tumor sizable enough to be categorized as stage 1, although you could have the signature up to 18 months in advance. Yeah, and so we've shown this, and we also have, for going to cancer, we also have the glutamate addiction. So there's one thing that tumor cells love to do is they love to eat glutamate. What they do is they plug it into the TCA cycle again as an intermediary known as alpha-ketoglutarate, or 2-HG. And alpha-ketoglutarate is, again, one of those subtle markers of elevation as the tumor starts to metabolize and consume the glutamate around it into alpha-ketoglutarate. That ratio between glutamate and alpha-ketoglutarate, if, again, indicated through time and sustained, could be a warning sign of another set of particular cancers. And we do the same thing with Alzheimer's. I have research in Alzheimer's now, a couple publications looking at Alzheimer's progression from normal controls with no evidence of disease, high pathology controls with plaques and tangles consistent with Alzheimer's but no symptomology. Those diagnosed with mild cognitive impairment, so they have the plaques and tangles and some symptomology, but it's consistent with aging. It's consistent with age-related decline in cognition. And then we have Alzheimer's disease, which is the full set. And by constructing our studies and getting from biobank samples that are from these known individuals with their associated clinical and demographic data, we're able to build these models and validate these models and show that palmitic acid and its increases are linear between these groups. And stearic acid is the same way. As the pathogenesis and symptomology increases, they ratchet up levels of these palmitic acids. And so when we combine not just 1 or 2 or 3, but 10 or more metabolites into a model for a specific disease, you can see it gives us a very hypersensitive and hyperspecific signature for that disease. So although one metabolite may be implicated in more than one cancers, the whole slew of metabolites in that model is specific necessarily to that type of cancer that we're profiling.